All right, lesson 2.9, logarithmic expressions, and this is a one-day lesson. So our skills and learning objectives are going to be to apply the properties of logarithms to evaluate expressions with and without technology of logarithms to evaluate. We're going to use the properties of exponents and logarithms to simplify and evaluate expressions, and understand each unit of the logarithmic scale is a multiplicative change of the base, 10 to the 0, 10 to the first, 10 squared, etc. Alright, so we know that the log expression log base b of n is equal to or represents the value that the base b must be exponentially raised to in order to obtain the value of n. That is, log base b of n equals p if and only if b to the p equals n, where n and p are constants, b is greater than 0 but not equal to 1. Recall that when the base of a log expression is not specified, it is understood as a common log with a base of 10. Alright, so what we have here is it tells us we have log base b of n is equal to p. Now I'm going to change it because most of other curriculums use different letters. So usually they'll use like log base b of x equals y, and then b to the y equals x. So we can change it from log form to exponential or exponential to log if we need to. It says there that n and p are constants. So that means our x and our y are constants, and our b has to be a positive number greater than 0, but it cannot be the number 1. Alright, and also it tells us that if we don't have a b written there, so like if I'm looking at the log form and b is not there, it just says log of x equals y, then it's understood that it's a common log, which means the base is 10. Alright, so here we have some basic properties of logarithms. You can memorize these if you want to. You don't have to, because being able to switch between log and exponential form, like I have written here in blue, we can solve all of them. So you can read through these, but you don't have to memorize them. Alright, so let's look at example 1. It says, give a reason for the following log expressions. And so it says log base 2 of 8 equals 3 because, well here, this is in log form. So we know it's log base b of x equals y. And we're going to change it to exponential form. B to the y equals x. So if I look at a, my base is 2, my x is 8, and my y is 3. And so if I change that to exponential form, I get b to the y equals x. And that's true. 2 to the third is equal to 8. So that's why log base 2 of 8 equals 3. B says that log base 3 of the square root of 3 is equal to 1/2. So we know that our base is 3, our x is the square root of 3, and our y is 1/2. So when I change that to exponential form, b to the y equals x. And remember, if you take the square root, that's the same as raising something to the 1/2. So that is true. Alright, C, my base is 5, my x is 1 over 25, my y is negative 2. So we have b to the y equals x. And you can check that because you know that 5 to the negative 2 is a negative exponent, so we're going to send it to the bottom. And so that does give me the 1 over 25. Now D is what they were talking about if you don't have a base written. So we can see on D that there's no base written here, and it says log, which means its base is 10. Okay, of x, which is that number 10 that I'm underlining, and then y is 1. And so if I set it up, b to the y equals x, we know that 10 to the first equals 10. Now be careful though, because e is in a different form. It does have the word log, but where is the word log at? It's up in the exponent. This is that exponential form. So this is my b to the y equals x. So my base is 6. My y is that log base 6 of 11 equals x, and my x then is 11. So because I'm in exponential form, I'm going to change and go to log form. So I have to write out the word log. Base b, which we said is 6, of x, which is 11, equals y, which is log base 6 of 11. And so that's true as well. So that's why all of these are true. Our example 2 says to write the exponential form as a log equation. So now they want us to go from exponential, so from b to the y equals x, to change it to log. So if we look at A, it says 4 to the third equals 64. So my base is 4. So this is b to the y, so my y is 3 equals my x, which is 64. So when I go to log form, I have to write out the word log, and then I know it's base b of x equals y. And if you want to do a real quick check of it, you can say, okay, well, 4 to the third equals the 64, and it works every time. All right, for C, my base is 2, my y is negative 5, and my x is 1 over 32. So we're going to log form, so write out the word log, base b of x equals y. And again, you can check it real quick. 2 to the negative 5 is 1 over 32, so we got it right. Whoops, I skipped over b over here. So b, my base is 9, my y is 3, my x is 729. So log base b of x equals y, and again, you can check it. 9 to the third is 729. And then D, my base is 64, my y is 1/2, and my x is 8. So log base b of x equals y. 64 to the 1/2 is equal to 8. So that's from exponential to log form. Then it wants us to do the opposite. Now we've got it in log form, we want to go to exponential. So now I'm in that log base b of x equals y, and I'm going to take it to b to the y equals x. So my base is 5, my x is 125, and my y is 3. So b to the y equals x. And just check it. Is 5 to the third 125? It is. All right, b, my base is 625, my x is 5, my y is 1/4. So change it to exponential, so b to the y equals x. And then check, is 625 to the 1/4 equal to 5? And it is. All right, C, my base is 1/2, my x is 64, my y is negative 6. So b to the y equals x. Is 1/2 to the negative 6 equal to 64? It is. And then D, my base is 2, my x is 1 over 32, and my y is negative 5. So b to the y equals x. And 2 to the negative 5 is equal to 1 over 32. All right, then it talks about common logs. It says logarithms with a base 10 are called common logarithms. The subscript 10 is often dropped, so a logarithm statement with no specified base is understood to be base 10. So we're doing the same thing. We're going to evaluate the following logarithms and exponential expressions. So notice on A, it's written as log of 100. So that's my log base b of x. And so I'm going to put equals y. So when I go through here, we're in that log form. So log base b of x equals y. And I want to go to exponential then to solve it. So I know that my base, it's not written, there is no small number there, but because it says log, I know it's going to be base 10. That's a common log. So my base is 10, my x is 100, and we're looking for y. So b to the y equals x. And then you got to see, can I get like bases? Will my bigger number go down to the smaller number as a base? Is 100 10 to the some power? And it is. If it wasn't, then we'd say, okay, well 110 both go down to the same base. But we know that 100 is 10 squared. So we have 10 to the y equals 10 squared. And because my bases are equal, we can ignore them. And that means my exponents have to be equal. So y is equal to 2, which means log of 100 is equal to 2. All right, b, log of the square root of 10. So this is in log form, so I'm going to put equals y. So my base, it's not written, it says log, so it's base 10. My x is the square root of 10, and y is what we're looking for, it's y. So I'm going to change it to exponential, so b to the y equals my x. Now I need to get rid of that square root. So remember, the square root is the same as raising it to the 1 over 2. So we have 10 to the y equals 10 to the 1/2. Again, my bases are now the same, or equal, so we can get rid of them. So that means my exponents have to be equal. So y is equal to 1/2, which means log of the square root of 10 equals 1/2. C, we're in log form, so I'm going to put equals y. So my base, it's not written, it says log, so it's base 10. My x is that fraction, and my y is what we're looking for, it's y. So b to the y equals my x. Now I need to get rid of that fraction, and so what I'm going to do is I'm going to bring that exponent, I'm going to bring that number on bottom up. So remember, anytime you cross a fraction line, you change the sign of the exponent. Right now that's a 1,000 to the first power on bottom, which when I bring it up means it's going to be 1,000 to the -1. Technically that 1 that's on top, it's being multiplied by it, but 1 times anything is just itself, so we don't have to put it. And I bring down my 10 to the y. Now, can I get like bases? Well, 1,000 go down to a base of 10. It will. It's 10 to the, I count the number of zeros. There's 3 of them. So it's 10 to the third, and I still have to the -1 there. Remember, power to a power. We're going to multiply the powers. So those exponents are side by side, and side by side in math means to multiply. So that's 10 to the -3 there, equals 10 to the y. Now my bases are the same, so we can ignore them, and we know y is equal to -3. So that means that log of 1 over 1,000 is equal to -3. And then finally D. D, notice it has the word log, but it's up in the exponent. This is exponential. This is that b to the y equals x. So I'm going to put an equals x there. And so my b, my base is 10 to the y. That's log. Let's change that actually. Let's change that to a base 10. That's a typo. That should be a base 10 there. And x is what we're looking for. It's x. So because we're in exponential form, we're going to go to log form. So remember, when you go to log form, you have to write out the word log. Base b of x equals y. And just like when my bases were equal, if my log bases are equal, I can ignore them. Okay, so I can ignore my log base 10s because they're the same. And so we know that x equals 6. So that means 10 raised to the log base 10 of 6 is equal to 6. Example 5 wants us to evaluate the common logs with a calculator. So we're just going to type it in. So if you look at your calculator, on the left-hand side, fourth button up, you should see the word log. And so we're just literally going to type in log of 34.5. And I got 1.538. then log of 0.43. So negative 0.367. And then I got log of negative 3. And it told me error. Which means it's not possible. There's no solution. And the reason is, we haven't talked about it yet, but that number there has to be greater than 0. It can't be 0 and it can't be negative. And it has to do with the graph, which we'll talk about in a few minutes. And so D, that's what it talks about there. It says, using your answer to example 3C, can you make a general statement about the log function? So remember, an exponential function looks something like this, right? And it's got that horizontal asymptote and y equals 0, okay? Logarithms and exponential functions are inverses of each other, which means, remember, we're going to switch the x and y. So I don't have a horizontal asymptote at y equals 0. I now have an asymptote at x equals 0, which means I have a vertical asymptote happening here. And so if I start switching all my x's and my y's, my graph is going to look like this. Okay, so this is the log function. Well, this one here is exponential. This one here is a log function. So you can see that my graph is on the right side. Nothing's over there in the negatives. And at 0, I have a vertical asymptote, so it can never equal 0 either. So that's why it has to be greater than 0. So logarithms is not defined. For x is less than or equal to 0. So therefore, the domain of logs is 0, not included, to infinity. All right, example 6 wants us to evaluate each log expression, if possible, without using a calculator. So it's just more of the same of what we were doing on the other. So notice we're in log form on A, so we are in log base B of x equals y. And so if we're in log form, in order to solve it, we're going to change to its exponential form, b to the y equals x. So I know that this is log, so I'm going to set it equal to y. So my base is 2, my x is 32, and y is just y. So b to the y equals x. Can 32 go down to a base of 2? It can. 32 is 2 to the 5th. I'm writing really big there. My bases are the same now, so I can ignore them. And so we know that y is equal to 5. So log base 2 of 32 is equal to 5. For B, I know my base is 49. My x is 7. And this is log form, so it's equal to y, so my y is y. So b to the y equals x. Can 49 go down to base of 7? Always check, will the larger number go to the smaller number? It will. 49 is 7 squared. The y equals 7. If you want an exponent there, it's to the first. We're going to multiply these exponents here. So 7 to the 2y equals 7 to the first. My bases are the same, so I'm going to ignore them, which means 2y has to equal 1. Solve for y. So we know that y is 1/2. So log base 49 of 7 is equal to 1/2. All right, C, we're in log form, so equals y. So my base is 1 over 64. My x is 4, and my y is y. So b to the y equals x. So b to the y equals x. Well, again, we did this earlier. We don't like fractions, so let's bring that up. So that's 64 to the negative 1 to the y equals 4. So I'm going to multiply those. So I got 64 to the negative y equals 4. And then I need to see if I can get like bases. So will 64 go down to a base of 4? It will. So 64 is what? 4 to the third to the negative y equals 4. I'm going to go ahead and put to the first. Again, can multiply my exponents. So 4 to the negative 3y equals 4 to the first. Now my bases are the same, so I can ignore them. So negative 3y equals 1. Solve for y. So y is equal to negative 1/3. And then D, I can start this. I know it's log, it's going to be equal to y, except for I happen to notice that what we're taking the log of is not greater than 0, so therefore this one is just not possible. If you try to set it up, when you do your exponential form, you'll have 5 to the y equals negative 25. You know, taking 5 to any exponent is not going to give you a negative number, okay? So that's why it doesn't work. All right, example 7, I want you to use your calculator to evaluate each log expression to 4 decimal places. So most of our calculators now have a log function on here. And so if you look under alpha, I gotta find it. Yeah, if you go to alpha window, and you'll see it says number 5 there, says log base. If you choose it, it will allow you to input a base there. So let's do that for the first one there. So log base 3 of 15. So input the 3 and the 15, hit enter, and you should get 2.465. All right, now do the same thing for B. All right, actually, it said to 4 decimal places and I only went to 3. So it should have been 2.46. Well, still would be 50 then. So, all right, then B. If you want to, you can just arrow up and still that the one you just did and then change it to log base 4 of 58. You should get 2.9290. And then go up and still it. Change it to log base 0.35 of 8.4. It should be negative 2.0272. And then D, same thing. So go up and still it. Change your base to 5/2 of 125. You should get 5.2694. All right, then orders of magnitude and logarithmic models. So it says use the order of magnitude to compare any like quantities. So using a calculator, we're going to compute log of 3 times 10, log of 3 times 10 squared, all the way to log of 3 times 10 to the 10th. All right, so log of 3 times 10. I got, whoops, didn't turn my pen on. Yep. So I got 1.477 log of 3 times 10 squared. I got 2.477 Log of 3 times 10. I'm going to do raised to the third. I got 3.477, and we'll keep going, and then log of 3 times 10 raised to the 10. And I got 10.477. So it says what pattern is in the integer parts of these numbers. So remember your integer parts before the decimal. So we can see it's just 1, 2, 3, and it keeps going all the way to 10. What is the pattern in the decimal point parts? Excuse me, it's the 0.477. And then it says how many orders of magnitude greater is 3 times 10 to the 10th than 3 times 10. So to find the orders of magnitude, we're going to divide these. So 3 times 10 to the 10th divided by 3 times 10. My 3's are cancel out, and this gives me 10 to the 9th. The exponent that the 10 is raised to is your order of magnitude. So therefore here the order of magnitude is 9. All right, then some Richter scale problems. It says the intensity levels I of 2 earthquakes measured on a seismograph can be compared by the formula log of I1 over I2 is equal to M1 minus M2, where M is the magnitude given on the Richter scale. Okay, so I is your intensity, M is your magnitude. Example 8 says, how many times more severe was the 2001 earthquake in India, who had a magnitude of 7.9, than the 1999 earthquake in Athens, Greece, who had a magnitude of 5.9? So it did just tell us that is equal to magnitude 1, which is 7.9, minus magnitude 2, which is 5.9. And then we can solve for the i's, because we know this is a log form. It's no base written, so we know it's log, so our base is 10. Log base b of x, so our x is the intensities, and y is 2. So b to the y equals x. And so we know then that 100 is equal to I sub 1 over I sub 2, which means it is 100 times greater. And if nothing else, you could take and you could actually multiply by the I sub 2. And you'll see that I sub 1 is equal to 100 times I sub 2. So the intensity of the first one, so the intensity of India is 100 times greater than the intensity of the one in Greece. All right, so the earthquake in India was 100 times greater than the earthquake in Greece. Now its magnitude of it was the exponent on that 10, so the magnitude is 2. But the intensity level was 100 times. All right, comparing chemical acidity with the pH scale. So the pH scale model, pH is equal to negative log of the positive hydrogen. All right, so it's a scale that measures how acidic or basic a substance ranks. The scales range from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. So we have vinegar here that has a pH of 2.4, and we have baking soda that has a pH of 8.4. What is their hydrogen ion concentrations? All right, so we have vinegar. Which its pH is 2.4. And so we could divide both of these by -1 to get the log part by itself. And then, since it is in log form, we know that our base is not written, so it's 10. Our X is the hydrogen, and our Y is -2.4. So we know that B to the Y equals hydrogen. And so if I type in 10 raised to the -2.4, and its hydrogen ion concentration is approximately 3.98 times 10 to the -3 All right, and we can do the same thing with the baking soda. So we know it has a pH of 8.4. My base is 10, my X is the hydrogen, my Y is -8.4. So B to the Y equals X. And so 10 raised to the -8.4 is 3.98 times 10 to the -9. This looks weird. All right, B says, how many times greater is the hydrogen ion concentration of vinegar than the baking soda? So we want vinegar to baking soda. Let's go put soda. All right, so the vinegar was 3.98 times 10 to the -3. And the soda was 3.98 times 10 to the -9. So this gives me, what's this, 10 to the 6th. And it tells us we're after the orders of magnitude. So remember, orders of magnitude is the exponent on the 10. So vinegar, because it was on top, is 6 orders of magnitude greater than soda. And that is the end of lesson 9.